Hi Bobcats. In this video we're going to look at the connection between pressure and volume for a gas sample, which is known as Boyle's law. And hopefully by the time we're done with this you'll be able to realize if you double the pressure, what happens to the volume, if you double the volume, what happens to the pressure, things of that sort. All right, so with Boyle's law, the very first thing that I'd like for you to do is to watch this video on YouTube. It's fairly short. This time of year, it's actually quite on topic because marshmallow peeps are involved. So pause this video, go watch that video. All right, hopefully now you've seen that video, and I'd like to talk about the particle picture of what you observed. In this illustration, we're looking at changing the pressure. Pressure is symbolized in this sort of drawing by the weight that's placed on top of the piston. So in this first one, we have a 1 kilogram weight, in the second one, a 2 kilogram weight, and in the third one, a 4 kilogram weight. Notice what happens to the volume. With a 1 kilogram weight, we've got a volume of 8 liters, but if we double that to get a pressure exerted by the 2 kilogram weight, we cut that volume in half, right? So up here, what we did was we doubled the pressure being exerted, and the response was that the volume was cut in half or multiplied by 1/2. Did that happen in the second, from the second container to the third container? Well, the pressure exerted was doubled because we went from 2 kilograms to 4 kilograms, and in response, the volume was cut in half. All right, so it looks like whatever factor we increase the pressure by, we're going to decrease the volume by that same factor. And when this sort of relationship happens, we say that the two variables, pressure and volume, are inversely proportional. Inversely proportional means if one goes up, the other one goes down. And when you do experiments like what's illustrated in the upper right corner, and you start trying to make plots of the data, you see things like this. The first plot was an attempt at looking for a relationship between volume and pressure, and we ended up with a curve. Curves can be really difficult to analyze mathematically, so a trick that scientists would use long before we had computers to crunch the numbers for us was to try to manipulate the data into some sort of form that would give us a line, because then we could make the plot, we could measure the slope, and we could figure out exactly what that relationship was. And so what people figured out was that if instead of plotting volume versus pressure, well, what you want to do is take the reciprocal of all of the volumes. So instead of taking 8 liters, you would take 1/8. Instead of taking 4 liters, you take 1/4. And instead of taking 2 liters, you take 1/2. And if you do that, you get a plot like what is shown on the right, which is a nice linear plot. So from analyzing all of this data, in the end, what we get is an equation that says P1V1 equals P2V2. So P and V stand for pressure and volume, and the 1s and the 2s stand for your initial set of conditions and then your final set of conditions. This whole process of curve fitting, which just simply means trying to find a mathematical function that fits your data, is really important in science. This is where all of the equations that you see to describe phenomena in science come from. And so there are certain mathematical shapes that are very well defined, like lines, parabolas, exponential functions, and logarithmic functions. But historically, lines were way easier to work with than any of these others, especially before we had computers to crunch the numbers. And so you'll see that very often in scientific data, we try to convert the data to some sort of a linear form. And very often the slope of the line has some sort of meaning. Now, in the case of Boyle's law, I'm not so sure that there's meaning to that slope. But for instance, if you were to make take a bunch of samples of a different metal and plot the mass of those samples versus the volume, the slope of that line would give you the density of the metal. And so you'll see that this happens very often in the 1141 and 1142 lab because this is a standard way of analyzing data. All right, let's take a look at an example using Boyle's law. It says that in the video with the vacuum pump and the bell jar, the balloon starts with a volume of roughly 2 liters at 760 torr. Once it's placed under the bell jar and the vacuum pump is turned on, the volume expands to about 5 liters. So what pressure was achieved in that vacuum system? All right, when I start doing problems like this, I like to make a variable list. You know, I clearly identified here that this is going to be Boyle's law, so I know that the equation that I will be using says P1V1 equals P2V2. What I mean by a variable list is I'm going to write down what numbers I have for each one of these variables. So I've got P1, V1, P2, and V2. So P1 would be the pressure initially. Well, it says initially our pressure is 760 torr, and our volume is originally estimated at 2 liters. After he reduces the pressure, well, there's not a pressure gauge on there, so we really don't know what that final pressure is, but we're estimating that the volume of the balloon in the end is about 5 liters. So now what I've done is I've identified all of my variables, I've identified what number goes with each one of them, and I can check units. I've got liters for both V1 and V2, that's good. With this kind of gas law, which includes what we'll do later is the combined gas law, it's really important that we have the same units for both sides of the equation. It doesn't really matter if we're using liters or if we're using thimbles. We just have to have the same unit on both sides. For pressure, we were given a value that's in torr, so that means that our answer will fall out in torr. Now, I prefer to do these by taking the equation that we were given and rearranging it to solve for the variable we're looking for. We're looking for P2, and right now P2 is multiplied by V2. So to get P2 by itself, I'm going to divide both sides by V2. Now I'm going to take this and rewrite it with the solved variable on the left-hand side. My 8th grade math teacher made me do that, and so I actually find it really difficult to write one of these final equations with the thing we're solving for on the right. So I'm doing 2 things to you right now. I am flipping this equation around left to right, and I'm dividing both sides of this equation by V2. So I'm going to have P1, V1 in the top and V2 down in the bottom. So now that I have it solved, I'm going to substitute the numbers that I have. So for P1, I'm going to substitute 760 torr. For V1, I'm going to substitute 2 liters. For V2, I'm going to substitute 5 liters. And whoops, I didn't really need to put just the liters in parentheses. All right, so if I run this in my calculator, I'm going to have 760 times 2 divided by 5. And that gives me an answer of 304 liters. Now, in terms of significant figures, probably should only keep 1. So really, if we're going to round this for sig figs, this should be about 300 liters. I'm kind of limited by these volume estimates that we started at 2 liters and ended at 5. So our objective for this video was to look at the relationship between pressure and volume. We know that they are inversely proportional, and mathematically they are described by Boyle's law. Eat 'em up, cats.